Today we will be doing with the Kirchhoffs law, and for Kirchhoffs law generally we use the Kirchhoffs law in those places where we cannot solve the simple circuits. Suppose if the electrical circuit has got uh, two or more cells with different EMF, then in that case it becomes difficult to find out the current in any of the register using the simple resistance and the current method that we generally use. So in this case, when the circuit is messy, it is complex, we use the Kirchhoffs law. Kirchhoffs law is mainly two types. First law is the junction law, we can call it as the rule. And according to this first law, we have got the sum of all the current entering. We will take as, because it is a junction one, so we'll take a point here. And suppose if we have taken a number of cells, this is I1. This is I2, this is I3, and let us assume this is I4. Let us assume this is the junction, and here the current is leaving, and here let us assume the current is entering. Here also the current is entering, and let us assume this is here also the current is entering. We can have another current. Let us take for example I5. It is just coming out. So we'll have our own sign convention. What is the first law? First law says that the sum of the current entering a point, sum of the current entering a point is equal to sum of the current leaving the point. So we'll have a sum of the current, that means the number of currents which is entering here is equals to the number of current which is leaving. So in order to do it, we'll have a sign convention, sign conventions. In the sign conventions, let us assume current entering, we have taken positive, and current leaving, we have taken this as equals to negative. So in this circuit, if we start from the very first one, entering means it is positive, leaving means negative. So if we get to see here, it is I1 is leaving, the arrow is outward, it is leaving. So it is minus I1. And suppose if we take this, it is entering we have taken as positive. So it simply means we'll write it as plus I2. Here it is entering, so it is plus I3. I5 is leaving is we have taken negative, minus I5, plus I4, because it is entering, I4 is equals to 0, or rather we can write I1 plus I5 is equals to I2 plus I3 plus I4. This is a very simple one, and it is being based on the conservation of charge. It is being based on the conservation of charge. This is the first one, we call it as KCL also, KCL loop also, we call it as KCL, Kirchhoffs current law. Kirchhoffs current law, we call it as Kirchhoffs current law. So this is very simple to understand. We have taken a point here, and here we have got different currents into the resistances, where it can take our own sign conventions, but the ultimate goal is that the sum of the current entering is equals to sum of the current leaving. Now suppose if we know the values of all, and suppose if the value of 1 is not known, we can easily use this method to get the value of this unknown current. So that is how we use the KCL, and in the numerical problem we are going to use it very often. Now the second law that we have, that is the second law. Let's do with the second law. The second law is also known as loop rule. This is the loop rule. Now in this case, when we write the loop rule, then what we really find that suppose if we take a closed circuit, what is very important here, we have to take the closed circuit, and we have got a generally in any closed loop. loop, the algebraic sum of the products of current and the resistance in each part of the loop is equal to the algebraic sum of the EMF in that loop. So what exactly, if I read the lines let us read the lines once again. In any closed loop, the algebraic sum of the products of the current and the resistance in each part of the loop is equal to the algebraic sum of the EMFs in that loop. Simply this is the statement, and then let us now see that how we can use this statement to find out the EMF or any other factor which we really want to know. Now in order to get it, let us have a circuit. Let's draw a circuit. Let us assume this is E1, this is resistance R1. We have taken another EMF E2, this is resistance, let us assume R2. And here we have got one more resistance. Now this is what we have got. Here we have got two EMF E1 and E2, and we have got resistance R1 and R2. Now in order to find, this is what if we get, let us assume this is R3. We'll consider there are two loops. We'll consider this as first loop and this is the second loop. Now when we see the Kirchhoffs second law, when we are doing with the second law, that this is based on the conservation of energy. It is being based on the conservation of energy. Since it is being based on the conservation of energy, then what we find that we will take one loop, the first loop and the second loop. We are going to get two different equations and we are going to solve this equation to get values. Now if we see the current, let us suppose here we have got the current I1, this is current I1, and from here we have got current I2. So here when this comes at this particular point, this is I1 and this is I2. So for all this it is I1 plus I2. Now this I1 for R3, the current that we have for R3 is I1 plus I2, because I1 is coming from here, I2 is coming from here. So ultimately it is I1 plus I2 here. And at this point also, this is the sum of the current I1 and I2. But at this particular point, what we find that there is a bifurcation in the current. The current gets divided into two parts. Let this part goes as I1 and this part goes as I2. So simply means that for the resistor R2 we have the current as I2, and for the resistor R1 we have the current as I1. So whenever we do with the circuit, we have to see how we can take up each resistor and find out the current flowing through it, and same way for all the resistor we have to do. And suppose if the EMF and all cells are given, then we'll have to take care of that as well. Now here what we really need to know, we need to frame two equations based on the two loops. Now when we have to frame the equation for the two loops, then we have got a general sign convention. So let us write with the sign convention. We'll write the sign convention. We'll take the potential drop as positive and we'll take the potential rise as negative. Now this is the sign convention which we are going to use. We are going to take the drop as positive and the rise as negative. Now let us see the circuit, and based on the circuit we have to write the two equations. Let us assume we have taken two different loops, loop 1. Now first in loop 1, No, when we see loop 1, no, see, here it is the resistor, and since the current is flowing through here, so there is a potential drop. So here it is taken as I1 R1 will be positive, and look at this point, here it is negative is lower potential, positive is higher potential. Once again I repeat, negative is the small one, the small line is negative terminal, so it is lower potential, and this is the higher potential. So what we find, when the current is flowing this way, then it goes from lower potential to higher potential, so there is a rise. So E1 will be taken as negative. E1 will be taken as negative. So we have got a very general sign convention. If we look into this, then here also we have the current I2. So it will be I2 R2 should be positive, because there is a current, there is a potential drop, and here also it should be minus low, there is a rise in potential, so it is lower potential to higher potential, so it should be negative. But if you get to see the sense of the current, then the sense of the current is not same. Here in this case it is in this direction, but here in this case it is just in the opposite direction. So suppose if I apply the general sign convention, if I write for this, we are writing for the loop 1, we are writing for the loop 1. In loop 1, we write for the loop 1, we have got I1 R1, and here it is minus E1, we write it minus E1, but in this case it should be plus I2 R2, and it should be minus. But since I have already explained, the sense of the current is not in the same direction, there is a change. So yes, although it is plus, but we'll write it as, because there is a change in the sign convention, so we'll write it as minus I2 R2, and here it should be negative, but I'll write it here E2 is equals to 0. Or I can write I1 R1 minus I2 R2 is equals to E2. If I take this as E1 minus E2, this becomes my first equation. This becomes my first equation. This is the current, this is I1, and this is I2. So this is my first equation. Now let us do with the loop. I just repeat once again. So it is I1 R1, and this is what we really have. This is I1 R1 minus I2 R2 is equals to, if it goes this side, it is E1 minus E2. Now let us do with the second loop. When we do with the second loop, in loop 2, when we look the loop 2, let us see this, we start from here. The current through it is I2 R2, it is positive, so it is negative to higher, lower to higher potential, it is again there is a rise in potential, so it is again negative. And since this is plus I2 the R3, and in bracket will keep the current, this equals to 0, because there is no EMF, and the sense of the current is same in all the direction, it is in the same direction, so there is no opposition. So we'll write here for loop 2, we have the equation, we have I2 R2 minus E2 plus R3 I1 plus I2 is equals to 0. So we have got I2 R2 plus R3 I1 plus I2, this is equals to E2. This is the second equation. Now we have got two different equations, one equation and the second equation. We can apply these two equations and we can solve our equation. So this is how we do with the Kirchhoffs law. This is the general way of understanding the Kirchhoffs law. There are two ones already told. The first law, that is the junction one. The second one is the loop rule. And we apply in the different circuit. Whenever you have the different circuit, I have taken only the values, but you may have 3 volt, 4 volt or whatever it is. To apply the general formation, just remember one thing, you can have your own sign convention. Here sign convention, I have taken potential drop as positive and potential rise as negative, and applying this we have got this relation. In this case, this was I1 R1 positive, there is a rise in potential here, it was negative, but here the sense of the current altered, they changed. So here it was positive, but then again it was substituted minus for the same reason, and then we have got this relation. So this way we have got this relation, and this next relation we can apply and get it the Kirchhoffs law, that we can find out the unknown values. Whatever value we need to find out, we can find out with the help of this. Thank you for watching this video.